The talk for today is the power of data-oriented attacks. The main idea for us is we try to get over the CFG control flow guard, and the technique we're using is the data-only attacks. There will be two portions for this talk. This is the first portion. We'll have another talk later in another conference. Here's something about us. This idea is actually introduced by our coworker, Bing Sun. He's a seasoned security researcher. Unfortunately, because of other commitments, he's unable to make it today. So myself and the coworker, Stanley, will be presenting this. Bing is the manager for the McAfee IPS security research team. And he has been working in the security field for many years, has extensive experience for operating system kernels and information security, especially in advanced vulnerability exploitation techniques for detection and offense as well. He has been also an active speaker for many conferences. My name is Chuang Xu. Currently, I'm a senior director for the McAfee IPS team. Our team has a lot of focuses, especially the attack technique that, as you can see here. And also, we do a lot of research for vulnerability research, malware research, APT detection, and also botnet detection. We also create the contents that feeds into a lot of the McAfee products. As a result, also, we have a lot of the things that we do for global threat intelligence that McAfee has. This is our coworker, Stanley Zhu.
Hello, everyone. My name is Stanley Zhu. I'm working on McAfee IPS research team. I'm interested in advanced vulnerability exploitation and compliance virus analyzing and antivirus design. Nice to meet you all. Let's us show our research for you.
Okay. Here's the agenda for today. We'll give a brief introduction about the CFG and the known methods. In the previous talk, it was already given a lot more detail. We'll go through it very briefly. And then we'll come to the main part of our talk, which is about the data-only attack. We'll give a couple of examples and then summarize what it is. Based on that, we'll give our suggestions to the prevention for data-only attacks. And also, based on those, the attacks and techniques we show, we'll give two demos that Stanley will show us. We conclude the talk by takeaways and acknowledgements. The control flow guard is one of the main mechanisms that Microsoft introduced for the purpose of mitigating the control flow hijacking. The implementation is, first of all, at the compilation time, compiler will insert the CFG check functions into the code. That will be right before each of those indirect control transfer, namely call instructions or jump instructions. And then the relative virtual address of all those valid call targets will be summarized and put into a bitmap. At runtime, this bitmap is loaded into the memory, and then all the call targets will be checked against this bitmap when we have this control flow guard in place. When the call target is determined as invalid, then that process will be terminated. That's the main idea of control flow guard. Here are some of the known techniques that can be used to bypass control flow guard. The first one is to corrupt the function's return address on the stack. We have the reference here. This is one of the works other folks did for that. The mitigation for this is to use the return flow guard or Intel's CET. The basic idea for that is you have a shadow stack. So when any return happens, the return address will be able to compare against that shadow stack, so that we can make sure that the address on the stack for return cannot be compromised. The next one is to do some kind of a transition via unguarded trampoline code. So this is mostly done by the dynamic code, especially for JIT. You can use JIT to bypass that. There are two works that we listed here. So the mitigation is obviously for JIT part is JIT security improvement. For example, you can do the JIT code checksum. So one of the attacks here is you first use the encoder to do the JIT generation, and then after that, that part of the code being generated for the native code will be copied to another memory for execution. But during this time, there's a gap, right? Then it's possible to change the code being generated. And if you add the JIT code checksum, then we can make sure that the code generated is actually the code that will be used for execution. Remote JIT is another idea where the JIT code can be generated from another process. Therefore, in the current process, then we cannot no longer change the code. Next one is the call function out of context. This is a relatively new idea, and here we listed two of the work that has been done previously. We'll give examples and also give another attack that we found for this. But the basic idea for mitigation is Microsoft couldn't really find a generic protection mechanism for this. So mostly those are fixed case by case. And sometimes those can be done through the fine-grained control for the control flow integrity check that we'll show later. A lot of the improvements were made for the Microsoft build 14.986. Will also show that what we have done and how the battle between the attacking technique and the mitigation technique works. As I said, this call function out of context can be one of the techniques being used. Now I'll show one of the examples that we found, what being found and reported to Microsoft. Here, what we're trying to do is to use this particular call. It's within NTDLL, it's RTL protect keep. What this can achieve is that we can use it to change the memory property so that we can change some memory that property from read-only to read and write. By doing that, then as long as we know where this control guard function pointer will be, then if we change that portion of the memory, then we can override the function to that. So that instead of pointing it to the function that Microsoft wants to execute, we point it to something that we want. In this case, as you can see here, what we're pointing to is a piece of the code that does nothing. Pretty much you jump to it and then you will return immediately. So if it looks like pretty much a null function. And then because we can change the pointer for this control flow guard pointer to that function, then every time this function is called, then control flow guard chat just returns, and it doesn't do anything. That way, we pretty much every time for every function that has the control flow guard, it can be bypassed. Here is the detail for the code that what we use. First of all, this whole sequence of exploitation is triggered through the JavaScript. But within the JavaScript, obviously, there are only things that you can do. You cannot call arbitrary functions that you want. But in this case, when we do the call out of context call, one of the assumptions is we have the arbitrary memory read and arbitrary memory write. Therefore, one of the things we can do is we find this function, as I said, the protect heap. For this function, for this call, then we can, through the arbitrary memory write, ask it to be pointed from the delete element of this array object. So when that's done, we will be able to call the operation to do delete array objects. And then when that's called, it will point to this RTL protect heap function, and this will execute. So this is the first step. And then obviously this step for this RTL protect heap itself has to be able to pass the CFG chart, right? Otherwise, then we won't be able to use it. The next step, what we do is we have to have the ability, or as I said, we need to change the memory property for the memory that points to this function pointer so that we can replace it, right? What we did is that within this RTL protect heap, it has two parameters. The first parameter is point to the base of a heap, and the second parameter is to tell this function whether or not we want to protect this portion of the heap or the memory that's in the heap, or unprotect it. Protect means we mark it read-only. Unprotect means we make it read and write. So that for the address that's been crafted in this heap, then we are able to make that piece of the memory writable. So that's the basic idea. Therefore, we ourselves crafted a heap, and then we put this particular address for that guard check I call F pointer into that in a particular place. Now let's continue to see how all those things work. We already know that this particular API, the RTL protect heap, takes two parameters. The first one is the base for the heap. The second one is what we pass in to tell it whether or not we want to protect or unprotect this particular heap that we point to. Internal for this is as follows. You can see it has two parameters, and also it calls this RTLP protect heap to do the actual work. Now let's continue to get into this function. For this RTLP protect heap, ultimately it calls this ZW protect virtual memory to change the memory property. So now we can see here is that, first of all, from the JavaScript, we call our delete element, but that is point to this particular protect heap call that we want to make. And then after all those crafted setting for the heap and also parsing the parameters of the heap base and also as the value to make sure that we want to unprotect the memory address that's in that heap, then we are able to trigger the whole chain of action so that we can make that piece of the memory which has the control flow guard check function pointer to be writable. Now you can see at the lower part that that piece of the memory after this it's already set to be writable. Now Stanley will give us a demo for us to see the whole attack process that we use for this particular technique.
Okay, let me show a demo for you. rigors that bypass CFG protection. So if we have AW or address right primitive, so it changed to AAW or AA right, arbitrary address right or arbitrary address read. Okay. Let me run the POC. We can simulate AAW or A right with WinDebug script. Attach edge process. First, let me check CFG got check iCal function. Obviously, the CFG got check iCal function pound to LDRP validated user call target. Let me run the WinDebug script. The script simulate vulnerability AAW. Okay. Oh, sorry. Let me show the video. We can leak the address edge NTDL base. And we can leak the guard check ICALL function address. Obviously, we can here we can see the CFG guard check ICALL function pointed to return instruction code. So the CFG protection had load the function.
Yeah, thanks, Xifeng. So what we showed is that through this vulnerability that we find for that particular call, then we are able to craft a heap, and then we are able to change the memory property, so that we are able to change the pointer that does the work for the control flow guard. Therefore, when the actual call happens, then it will point to something else instead of the original control flow guard the call. So that's how the call out of context actually works. Microsoft did the fix. What it is that for that particular RTL protect heap, it make it the call target, it make it unable to parse the CFG check. So that's why in this case we no longer can use it, because as we said, one of the assumptions is that we have to find a call that can bypass the CFG check to start with, so that we can no longer, in this case, since it's no longer a valid target, then we cannot use it anymore. That was fixed in the build 50048. So to summarize, for the basic idea for core function out of context is we have to issue a function call to the unexpected target. In this case, the execution logic for the original code is changed. So from that perspective, it's one type of the hijacking of the original control flow. In order to make this out of context call to be successful, so the idea is first of all, you have to override the existing function pointer. We already showed that the function pointer we override is the control flow guard, the check function. And then the target function has to be able to bypass CFG check. That we already also said. The original protect heap function that we use is able to pass the CFG check. One of some other important factors is that because we are exploiting this at the JavaScript level, at the scripting level, so that means that for whatever the native calls you get, you have to be able to invoke that call repetitively and also successfully, especially for some of those, because ultimately the call that we want to use might have different parameters, but we have to be able to pass the parameters that we need into it, and we have to control the use of those parameters before the real work was done for that particular function that we called. That's very important. As we see in our example, we crafted the heap, and we put the necessary information into that heap so that we parse the base to the heap and also the flag that we want to protect or unprotect the memory that we want to change. So those are the two parameters that we have to be able to control. Otherwise, there's not really much we can force that function call to do the work for us. Sometimes that for such a target function, the return values are also important. If in some cases we need, for example, if the return value we are expecting an address, then we have to be able to control to get the ultimate return parameter as well. But if the function we called in this case is say the product keep, then it returns some parameter that we want to use later. Say if it's an address, then we have to be able to get it at the script level. Otherwise, then although you can force things to happen, but you don't get the information you need to continue. So that's also very important. One of the good examples for the previous work is listed here, from read and write everywhere, anywhere to controllable calls. If you guys are interested, you can check out. Also, it has a very good example of this function called out of context technique. Okay, this has we have shown a lot of the work done through this call out of context. So Microsoft has did a lot of improvement also in order to counter that. In this case, for the control flow guard, as you can see, some of those, especially the call out of context, is no longer within the scope of this Microsoft bypass bounty program. Then what do we do? This technique is being patched and also is out of the scope. Then we have to find a new way to continue our attack. Then this is where we think the data-only attack will be coming into play. And going forward, it probably will play a very big role in the attacking technique. What is a data-only attack? The basic idea for data-only attack is that for any program, there must be some meaningful data that will be used. Such data can determine what the behavior the program might be. But we're not trying to change the control flow as we see in the out-of-context call, because we're not changing the pointers to point to something different. The program will still execute, but then because we changed some of the data that controls the flow of this execution, then we'll be able to change the behavior of the program itself. Because we're not changing the control flow by forcing it to go some other routes, right? Therefore, the program logic still remains the same. Therefore, in this case, the control flow integrity check is no longer in the picture of the attacking technique we use. There are two very good examples for this attacking technique. One example is the vital point strike. It's called the JavaScript God mode. Basically, you can change piece of the flag within the memory so that your JavaScript, instead of running with some limitation, then will run as arbitrary code that you can let it to run. So that's controlled by a piece of flag in the memory. Another example is to bypass EMAT. EMAT, the biggest idea here also is there are some data that controls whether or not EMAT is enabled or disabled and how it's been used. But that data is protected and it's encrypted, and also the address is stored somewhere else. But unless you can have the ability to decrypt that, then you won't be able to touch that piece of memory. So this technique actually used some brute force to be able to get the encryption key out of it, and then everything else is very obvious. So those are the two very good examples. Then for the data-only attack, then what are the data portion of the target that we want to use? There are several of those. First of all, the example I give is some of the global flag or maybe some object that of the data that will determine how the control flow will go to this way or to that way. So those are the things that we need. The vital point strike is a very good example of one flag in the memory will determine what your program is able to do. And then for the second bypass, for the EMET bypass, actually is a piece of memory you want to change, but there are other ways to get access to it. So those are the things that we want to look for to start with. And also other unprotected data section or unprotected heap of private data, including stacks. Those are also the things that we are very interested in. So we know that what the data-only attack is and some examples and what are the things we're looking for. Now, how do we launch such an attack? First of all, as I said, a lot of the current attacks all require the arbitrary memory address read and write. So that's one of the assumptions we have. And then for us, because we want to locate the data and change the data, obviously the location of your target data being changed or manipulated by us is very important. So that's the key to our success. That being said, some of the data might be transient and some of the data may have to be very time sensitive. For example, if you're trying to change some data, if it's, let's say, some local variable, then it only is valid within that particular function call that we want to see, right? Or another example can be the example that we showed previously. When the JIT code is generated to the point that JIT code is put into memory to run, then there's a gap between the time. So that's the only window that you can have to change that. A lot of the times, such data are protected by locks. When that data is being changed, that lock is unlocked. But then after the change of the data, then the lock will be applied. So you only have that very small window that you can use to change that data. This is one example we had last year for the data-only attack. The basic idea is for the graphic generation, nowadays there are hardware to do that, but in the old system or some other system, or even in a system that has the hardware support, you still have this software counterparts just in case the hardware is not there or is not supported for some of those. That's called warp. And then we take advantage of the warp shader, which is used to render the 3D data into the 2D dimension. We use that to do our JIT spray. Obviously, not all the warp is enabled by default, right? We have to force the enabling of this warp in order for the warp shader to work. That means although the hardware may support the graphics, but then we want to disable the hardware and force the system to run the software version of it so that we can use this warp shader to do the heap spray for us. We reported that to Microsoft. As I said, because we're trying to enforce the loading of something that's not being used by default, then we have to change some critical data in order to achieve that. We reported that to Microsoft, and Microsoft had the first fix in July last year. Those two references, you can take a look, especially the second one, it has more detail of how we did this to start with. And then later on, Bing found out that although Microsoft had the fix, but actually we still can bypass it. The reason being that their fix is rely on a global variable. But then, as we know, global variable is piece of data. If we can locate that and if we can change the content of that global variable, then we'll still be able to bypass this. And he reported to Microsoft again, and ultimately in December, then that was ultimately fixed. So this is, as you see, attacking technique and the mitigation techniques is in a battle for this. And in this case, it's seesawed multiple times for us ultimately unable to use the technique that we have. Before the fix, the first version for this particular build for the DLL, for WAP DLL, Microsoft actually, when the JIT code is generated, there's no control flow guard check for that. There's no integrity check. So which means everything we generate, it should be a valid target address. And all the things that we have after the JIT code generation, we can jump into that because all those are valid addresses. That's why the first attack that we have is very successful. And then Microsoft had the fix in June of last year. As you see, what Microsoft rely on is a global variable. It's called is CFG enabled. If the CFG is enabled, this flag is set, then going down, what it will do is that for all the JIT code that is being generated, then it will set the target for as valid for those. So when that is done, then that means only those entry points for those functions being generated are the valid targets. We cannot jump arbitrarily into the middle of those code. So that limits the ability to launch attacks. But since this is still a global variable, as I said, it's a piece of data. As long as we can identify where it is, then we'll be able to change it so that we can make this set process valid core target not being invoked. Then we're backing to the original version if that's the case. And then ultimately, Microsoft had another fix. Instead of relying on a variable, now everything is done through a function call. In this case, because it's no longer depending on any particular data, since it's a function call, then we can no longer use this data-only attack to continue. So this is a very good example, as I said, that battle between the attackers and the mitigation mechanism continues. Especially in this case, is the data-only attack. Now, since that is not feasible for us anymore, then what we do, we find another way to execute our code, arbitrary code that we want. The way here is, first of all, we want to use ActiveX. As we know, say Edge and all of those ActiveX are disabled by default. So then what we need to do is to force the launch of this, and then as we can see later, it's still whether or not a feature is enabled is stored in some called a feature cache. And then as long as we can find that feature cache and change it, then we can change the behavior as whether or not this ActiveX extension can be loaded. The thing we use is Silverlight. One of the good things is Silverlight, when it's loaded, then it will create a piece of memory which has the read and write and execution property. So as long as we can force the load of Silverlight, then we will be able to get a piece of memory that we can read, we can write, we can put our code to execute. All those, the address will be valid for any of the execution we want. As I said, by default, Edge disabled the ActiveX. And not only Edge, some other things, say BHO, VML, or VBScript, and also by default, they're cannot be used, so that the Edge itself has a significant less attack surface. In order to force the Silverlight to be loaded in Edge, there are two things that we need to do. Especially, those are either the checks that we need to bypass, or those are the flags we need to reset. The first place is has something to do with the feature cache pointed by this URL among GP flag cache pointer. Within that, when the ActiveX is being initialized and instantiated, then there are two calls to check whether or not this is valid. The first place is the Edge HTML CLA site, the create object security check. And the second one is the URL among is ActiveX extension allowed. But both of those checks actually call the same function to do the work. That function is CO in internet extension allowed for URL. We'll see later in the code then how this is done. The second, this piece of the check, actually what it does is that it checks the 14th entry in the feature cache to determine whether or not that internet extension is allowed to be loaded. So we know that feature cache is managed by URL among.dll. Therefore, the only thing we want is to see how to manipulate those. The next check is the COM-base get load library altered and search path flag. So that flag also determines whether or not the DLL loading can be successful. For the success of our attacks, we have to be able to set this particular flag to something we want. In this case, it's load with altered search path. So now let's look at the code, how this works. Oh, this color. Sorry, the color seems to be a little off. Basically, this light shows that this is the first call that we have to bypass in order to successfully launch the Silverlight. It's marked in red. And this is the second one we have to be able to bypass. And both of those, as we said, it points to, it calls the URL among the CO internet extension allowed for URL. And what it does, as we can see here, is it will search for the look for its 14th entry and to do the check for this feature. This is the detail. First of all, the first portion points to that feature cache, and then we compute the entry, which entry we want to test. In this case, it's the 14th entry 0D in binary. And then we see what the value is for that particular cache. So what here is, we know that where that feature cache is, here's the address of it, and we know is the 14th entry. So that piece of memory that's marked, then that's where we want to change it. And then, as we can see, it's writable. So it yeah, that's why that piece of the feature that we can, because of the writable, then we can change it. And then when as I said, when the DLL is loaded, then we need to set the other flag so that we can allow the successful loading of this. This is the whole call stack. In this case, now it comes to here. We see that DW flags is actually where the flag is. So what we need to do is when the kernel base load library exw is being executed, we want to parse it to the other value that we want so that this load DLL can be successful. Here, we know this code tells us where that particular flag is stored. So it's a flag that's stored in the global library within the com-base.dll. Then the only thing we need to do is to change it. The default value is 0. 0 means that it cannot be loaded for that particular library. But then if we change it to 8, which is a load with altered search path, then we will be able to load the Silverlight plugin, which is the NP controlled DLL. So here you see that we is able to change that particular flag. Now, after we change the flag, so we bypassed all those two places we just mentioned. Therefore, as you can see, that we can continue to load this library. When this library is loaded, then one of the things it does is it creates the read-write executable memory. This is where we can see from the bottom part that this piece of the memory is read-write executable. So in this case, as long as we can figure out where this memory is, then we'll be able to write code to it and jump into it for the execution of our instructions. Microsoft kind of fixed this, but it's a generic fix by the arbitrary code guard. It's not particularly fixed for the approach we use. The arbitrary code guard can prevent the load or execution of some of the libraries. That's why it's in some ways a generic fix. In this case, when the arbitrary code guard is on, and then np control.dll cannot be loaded because its p files import table, the .idata section, is marked as a read and executable only. And also, even if, say, we can find a way to load this, but we still cannot make it to generate the read-write executable memory. But since this is rely on the arbitrary code guard ACG, then what if we can disable it? Then the ACG will be gone. Then the old technique we use will still be successful. Therefore, in the build before this build 14.9.86, we can do the opt-out so that we call this kernel 32 set thread information with this parameter thread dynamic code allow equal to 1. Then that will opt out this process from this arbitrary code guard, and then everything else still remains the same. So let's now see the demo of how this works in reality.
Okay, to save time, I show demo. I show video. We target goal how to force the servlet DLL to be loaded in Edge. We know the Edge block anything ActiveX into Edge price. We can see there are no servlet DLLs in this list. We can see there are no read-write X memory in this list. There are no RWX memory. Once the servlet DLL loaded, we got RWX memory in Edge process. Detach WinDebug. Here we can see the servlet DLL to be loaded in Edge process. Servlet DLLs. And we got RW write memory. Here we can see execution read-write memory in Edge process. After then, we can copy shellcode to here and control everything target machine.
Okay, thanks, Stanley. So now we see that in action, we were able to use the data-only attack to change some of the memory locations for the data portion. And then that allows us to do the things that we want in a normal way. We didn't really change the control flow by forcing it to go different routes. We only changed the data so that the execution is still executed in a normal fashion. We know that this is a technique that can be very powerful, but then what are the suggestions for prevention? The most important thing is never let the critical data unprotected. As you guys can see, some of those data are in the read-write memory, right? And some of those are in the readable only, but we were able to change the memory property so that we can change the data that we want to manipulate. For any critical data or the page that we want to have the right protection to it. So that's one of the most important things. Only when that data needs to be changed, then you unlock it, and then after the change, immediately lock it again. So that will greatly reduce the possibility for attacks, but still, because there's a gap between the last write to the lock of the data, that's why we still need to be very careful. In some of the cases where the lock is not feasible, because, for example, if the page is constantly being used, then what we have to do is we want to encrypt that piece of the data and then keep the address in a much safer place. For example, you put it in the kernel in some way. And also for the critical data that we use for where it is stored, we want it to be dynamic so that ASLR can be used for that purpose. If we want to encrypt that data, obviously the key for the encryption is very critical. And also the encryption algorithm can be very critical too. Another thing that is very important is in the program that this is more of the operating system. Then always check the integrity of the critical data. It's either by operating system or by the program, so that you make sure that the critical data is not tampered with. By doing that, then we're able to prevent a lot of the attacks from being successful in early stage. So the main takeaways for our talk is that with a lot of the enforcement for CFI solution, then the call out of context approach will become less effective. And then therefore, there are still a lot of the data in the operating system that are unprotected. That can be used to launch attacks. In this case, is the use of the data-only attacks. Data-only attacks didn't really force the change of the execution flow, but it uses different data to allow the execution goes the way that we want it to go. Even if the attack is well known and probably aware by a lot of people, but it's still difficult to prevent that, especially in some cases. Say some of the data and data structure being used, it can be very normal. There's no way for us to distinguish which is the normal data, which is not the normal data. For example, if you rely on certain number of array entries, then whatever the array entry being put there can be manipulated by the attacker or can be put in there by the operating system. So there's no way for it to distinguish. And then for the data, we want it to be as safe as we can. Sometimes we want it to be in the kernel, but even if it cannot be, then as we said, we want different encodings, different protection mechanism, say encryption, to protect those. Data-only attack, the one we show here, and also the examples are being given, it's mostly you write certain memory to change the property of the data. But then there are some other variations. We will, in our next talk, will see how this can be done through the race condition so that we're able to change the behavior of the locks. So that pretty much concludes our work, the talk. Those are the contact informations. We would like to thank the MSRC for those bug fix and collaboration with us. And also, we would like to thank our team members from the McAfee IPS vulnerability research team, especially Haifei Li. Now, those are the references for the things that you guys can take a look. So that's pretty much for the talk, and we're open to questions. Okay, no? Okay, then thank you, everyone.